Okay, so now the question is, how do we relate the percent reacted to equilibrium? So relate percent reacted to equilibrium. Okay. Keeping in mind that delta G is equal to the change in the Gibbs per change of extent of reaction. Real quick on this, delta G of reaction, this represents A going to B, okay? There's a delta G associated minus. All right, so the delta G of reaction is the fact that you've got the delta G of formation. Let's just say delta G of formation. Delta G of formation of B. The difference in the products minus the reactants. That's delta G of reaction. Here, I'm talking about the Gibbs at that particular point. There's a certain quantity of energy, not the state function aspect, but the certain quantity of energy that you have along the reaction core, along the extent of the reaction. Okay, so this is equal to the slope at any point. Okay, so there, delta G equals 0. Okay, whereas these delta G's of formation are from, they themselves are reactions, okay, because you'd have the elemental form of whatever this component is yielding that, the formation reaction of whatever B might be. Okay, sorry, side note. We want to relate the percent reacted to the equilibrium. How do we do that? FYI, ice tables are coming. Why do you learn ice tables in every class? Because they are freaking important to know. Then they are very, very helpful to do. Okay. So we're going to introduce the term alpha, which is our degree of dissociation. And I believe you have done this kind of to the same extent in analytical, but I want you to link these ice tables that you're going to do to the thermodynamic properties that we've been studying thus far. So alpha is the degree of dissociation in terms of total pressure. In terms of some final pressure. Okay, so alpha is equal to n minus n equilibrium divided by n. So at any given point, there's going to be some extent of reaction that that's undergone, and you're going to be relating that to what your equilibrium condition is. Okay, so if at equilibrium all of A has reacted, then n equilibrium would be 0, which means, so if at equilibrium all A has reacted, that means n at equilibrium is 0. There's no more A left. That means alpha is equal to n minus 0 divided by n, which means we're at 100% dissociation. Okay? If, however, you have, let's say, 0.0001 is the amount of equilibrium, n minus practically, well, or sorry, so if n equilibrium is close to n, then that means at equilibrium, we haven't really changed much of anything. This means this is essentially 0, which means that we are nowhere near the extent of dissociation. Cool? Okay, so the two extremes. Nothing has dissociated whatsoever. There is no equilibrium condition that we can reach, and we have completely gotten to our equilibrium condition. Okay, so I'm going to give this, I'm going to take you through creating an ice table through an example of, let's see, NH3, and then hopefully you can follow along with what I do. Okay, so here's our example. We've got NH3 decomposing into nitrogen gas and hydrogen gas. And our equilibrium constant, 1.68 times 10 to the minus 6. Really quickly, let's think about what this number means. So if this is the ratio of the activities of the products to the reactants, this is a very small number, which means equilibrium is going to lie very far this way. Go team. This way. So ammonia is not going to degrade easily to nitrogen and hydrogen gas. Okay. So alpha is the fraction of NH3 that's reacted at equilibrium. N is the initial total number, or the initial number of moles of NH3. So that would be something that we'd know. It's a quantity that we could start with, so have knowledge of initially. Okay, so that means that if this is the fraction of NH3 that's reacted, N times alpha equals the number of moles reacted at equilibrium. Okay, so now we're going to set up our ICE table with the question of we want to determine what is the equilibrium pressure. So here's the question. So what is equilibrium pressure of N2H2 and NH3? So we want to know at equilibrium, what are their pressures? All right, so we're going to set up an ICE table. And actually, I'm going to erase these two things so I have more room. Actually, I'll erase these three things. All right. So we've got NH3, N2, H2. And we've got the initial. And we've got equilibrium. And I say an ICE table, kind of. So the initial number of moles that we have, we're going to start with N. And we start with 0 and 0 of those. And then the equilibrium number of moles we have are N times 1 minus alpha, and alpha divided by 2, and alpha divided by 2 multiplied by 3. Okay, why have I written it this way? So if you want to think about, actually, hang on. Okay, so if you want to think about how the change, we'll add that in. So here we've got minus N alpha. And so if N times alpha is the number of moles that have reacted, or the fraction reacted at equilibrium, then you're going to have, so plus N alpha plus N alpha. Actually, that's not entirely true. So you're going to take into account the number of moles you have multiplied by the percentage that's reacted, and then you're going to subtract these two, and that's going to give you N minus N alpha, which I've just simplified to N times 1 minus alpha. Okay, and then here you've got plus N alpha, but for every 2 moles of NH3 that are reacting, you're creating 1 mole of NH2, or sorry, for every 2 moles of NH3, you're making 1 mole of N2, so that means you're going to have a half N alpha created, okay, because of the 2 here. And likewise, you're going to have 3 N alpha created per every 2 NH3. Okay, so there's your ICE table, initial change, equilibrium. So now, at the total number of moles at equilibrium is equal to the sum of those. So you've got N times quantity 1 minus alpha plus N alpha divided by 2 plus 3 N alpha divided by 2. Okay? And so all of that, if you write this out, equals N times quantity 1 plus alpha. That's kind of nice. So that means that the mole fraction at equilibrium will then be N 1 minus alpha divided by N 1 plus alpha. So this is, actually I'll color code this. So you've got the number of moles at equilibrium divided by the total. So there's number of moles. So this is N in H3. So N in H3. Then you've got N alpha divided by N 1 plus alpha. And this would be that one. Oops, there should be a 2 there. And then likewise 3 n alpha divided by 2 n times 1 plus alpha. Oops. Okay. So now, and then likewise n of h2 divided by n total. So each of these are the n totals, n times 1 plus alpha and n times 1 plus alpha. All right. Everyone following me? Go team. So now I want to convert this to the partial pressure. And I know that P total times the mole fraction is equal to P of each of our independent components. And so if this is the mole fraction of NH3, then that means that P total times the mole fraction of NH3 is equal to the pressure of NH3. Does everyone follow that? So what I can do is I can multiply each of these quantities by the pressure, and then I would have a relationship for K sub P, which is the equilibrium constant at constant pressure. So this is the pressure of N2 times the pressure of H2 divided by the pressure of NH3 raised to the appropriate stoichiometric coefficients. And these are the partial pressures of each one. And so I would take then the total pressure, multiply that by each thing. And so I'd get, I'll do it this way. So pressure times this, pressure times that, and pressure times that, which would then yield and I'm going to have you go through all of this and verify that I am right. 27 divided by 16 alpha to the 4th pressure squared divided by 1 minus alpha squared, all of that squared. Go team. You can see why I'm not doing this outright. And that equals 1.68 times 10 to the minus 6. Sweet. And so if we say that the total pressure is then 1 bar, you can then solve for what alpha is. All right. Okay, so you'd solve for what alpha is, and then, so you'd solve for alpha, because notice how there are no n's of N2, H2, or NH3, or the total, or the vapor pressures of each one. It's all in terms of alpha. So you solve for alpha, and then use the equilibrium values, which were, say, for the mole fraction, you'd say for NH3, you'd have N1 minus alpha divided by N1 plus alpha. So whatever your alpha value is, you would then put that in, and then from that you would be able to determine what your NH3 is. Cool? Okay. Why did I go through all of that? Because there are some important aspects of recognizing how do you approach figuring out what your system is. That's the same thing that we've been studying this whole class. Is it an ideal gas? What's the process? Is it isothermal, isochoric? What parameters are staying the same? What parameters are changing? Now we're introducing a new direction or a new degree of freedom that we can go down, which is that extent of reaction. Okay, and as we get closer to that delta G equals 0 moment or equilibrium, we're going to have the reaction quotient changing. And as it changes, it's going to get closer and closer to representing the equilibrium constant. And that equilibrium constant has information contained within it about how the chemistry is actually occurring. Cool? And so how is the system progressing through the reaction. How is it approaching equilibrium? These pressures and these concentrations that you get from thinking about things in terms of extent of reaction, or this alpha here, is really helpful in characterizing and classifying your systems. Cool? Go team. All right, that does it for the videos for chapter 6. Woo! Go team.